Welcome back. So we're in the process of learning some different techniques, and what we've learned really is that with some differential equations, basic ones, we can just integrate. And then we had a couple other classes like separable equations and then some linear first order differential equations. And now what we're going to do is look at some that don't particularly fit those models. So we have a whole bunch of ideas that we wrap up into this concept of substitution techniques. So here's our plan for this. When we get some things like we don't particularly recognize as just a basic integral or separable or linear, maybe we can substitute to make it into those things. And then there's a couple other ones where we do a substitution and they're their own thing. So what we're going to be talking about are these substitution techniques. And the first one we're going to discuss is homogeneous equations. How to make that substitution to change a homogeneous equation into some technique we've already learned. For instance, just a basic integral or separable equations or linear equation. So that's the idea. Now, these substitution techniques usually fall into one of five categories, and then we have something that's called exact equations, which we'll discuss later. So here's our five classes of when we might consider doing a substitution. Number one, what we're going to talk about today is homogeneous equations. How to make that substitution. I'll discuss exactly what we do with that. Next, we could have an obvious substitution. Now, that word is deceiving because every time I read obvious in a math textbook, it wasn't obvious to me. It's like, what? The proof is obvious. Not necessarily. So, obvious, I'm going to use that term loosely. The idea is that we have a composition, and if you can see the composition and make a substitution for it, then we can oftentimes do that substitution, create something we all already know, like linear or separable equations. So, homogeneous first, that's today. Then we'll talk about obvious substitutions, we'll talk about Bernoulli equations, we'll talk about embedded derivatives. So when part of your function, a differential equation, has a derivative of the y piece in there, we can oftentimes do a substitution that's really nice, save us a ton of time. In fact, in the first example I do today, it's going to be done both ways. So I'll do it today with homogeneous, and then in another video I'll show you how it actually has an embedded derivative. It would have saved us about 10 minutes of work. So I'll show you that. So next, last we'd have reducible second order differential equations. You might have been wondering, do we ever deal with second order? Very special cases? Yeah, we do. We can. And so we'll talk about that. So a little recap, we're only a couple minutes in, but we're going to start making some equations that we can't directly attack into something that we hopefully know how to deal with. And that maybe involves a substitution. So for us, it does involve a substitution. We're going to get to those. So we have homogeneous, we have maybe a composition where it would be an obvious substitution. We might have a Bernoulli substitution that we can make. We could have an embedded derivative, or we could have a reducible second order. And the last class that's not up here is exact equations. So we'll look at an exact differential equation a little bit later. The one thing I mentioned about this one, I'm going to give you an example in just a bit that can be done two different ways. And so when I tell you about these substitutions, I don't want you to think that every differential equation is going to fall into one and only one of these classes, because that is not true. As we go through these videos, I'm going to make certain, because I'm going to do several problems, 2 to 3 different ways, to show you that, well, while we might be able to make it homogeneous, maybe a Bernoulli would be easier. Or while we might be able to make it a Bernoulli, maybe an embedded derivative would be easier. Or they fall into several classes. So take the one that would be the easiest. How you do that, how you determine which would be the easiest, that takes a lot of experience. And so when we're going through these, you're going to notice that some techniques are easier for certain problems and some techniques are not easier for certain problems. So that's why I'm going to be doing several ways, and you can take your pick. So my thought process right now is to kind of get us out of this mode of, wow, there's going to be one technique that works for this one type of problem. That's not true. A lot of these techniques cross over. So let's explore right now homogeneous equations. I'll show you exactly how they work, and we'll go through a few examples. And then in the next video, what we're going to do is we're going to just do a ton of examples to explore a lot of different possibilities with these homogeneous equations. So what are we looking at? What does a homogeneous equation mean? Well, it means this. If we can write our differential equation as this function where we have these fractions, y over x. So every instance where we have a y and an x, we can make it into y divided by x, and that can appear a lot of different places. So if you can solve for your first derivative, if you can solve for that dy dx, and if you can make this function into y over x and then y over x everywhere, well, then we can make a substitution. So the substitution says, what if we were to suppose that instead of having y over x everywhere, we called y over x this v? Why would that be so important? Well, it's because if we solve this for y, then we can make a double substitution. And I'm going to show you that right now. So step one, I'm going to give you the steps as we go through this. Step one, a homogeneous equation is when we can write our differential equation as dy dx equals a function where we have y over x in every instance of our y. Okay, we'll make our substitution. Let's let v equals y over x. Why do we do that? Magic, because I told you so. Not a good answer. If we solve this for y, which it would give us y equals v times x. I'm just going to show that over here. Well, y equals v times x, then notice something. We'd already have all of our y's wrapped up into this substitution, so every instance of y has to have a y over x. Well, what that means is that we can wrap up y over x as this v. So every time we have a y, we'd have v, and y over x, v, and then v, and then v. But that's a problem because we'd still have a dy dx, but then this would not have any y's in it. So we wouldn't be able, we'd have basically three variables. We'd have y, then we'd have v, which is a function of y and x, and then we'd have x, and that would be really difficult to deal with. But if we solve v equals y over x for y, well, then maybe we can take a derivative right here, and it would be an implicit derivative on v. So notice something, when you take that derivative of v, you're going to involve a chain rule. You're going to get that whole derivative of v times dv dx, because that's going to be a function of y and x, but the independent variable is x. That was a lot of words, so I'm going to show you right now. So long story made hopefully a little bit short. Hey, dy dx equals function where you got y's over x's. Make sure that your v covers every instance of y. It's got to be y over x. Okay, that replaced all of our y's, but that still has a y. So let's solve for y. Let's take a derivative on both sides with respect to x. Well, on the left-hand side, we would get derivative of y with respect to x. Yeah, that's an implicit derivative of y. Y is a function of x, so we're assuming, and so we can do dy dx. But on the right-hand side, when you take a derivative of a function that involves x's, right there, and x itself, that's a product rule. So we can do the derivative of the first, but wait a minute, it's not just one. This went back to Calc 1 when we did implicit differentiation. You said, well, v is really a function of x. Yes, it has y's and x's, but y itself is a function of x. So you go, okay, let's take a derivative of v. How would you do that? You would take the derivative of v, which would be 1, but then you'd have a chain rule, times the derivative of whatever that function of x is, dv dx. So we do the derivative of the first, 1 times dv dx, times the second, plus the first, that would be v, times the derivative of the second. Since x is our independent variable, we don't need a chain rule on that. If you did a chain rule on x, you'd say derivative of x, 1 times dx dx, that's the same thing, that's 1. So the derivative of x would just be 1, so this would be times 1. Let me show you this in a little bit more detail. If you took a derivative with respect to x of y and v times x, the derivative of y implicit dy dx, that's where this is coming from. The derivative of v times x with respect to x. That's a product rule, because that is a function of x, that is a function of x, so derivative of the first, 1, but chain rule implicit, dv dx, that's this, 1 times dv dx. So product rule, derivative of the first times the second, there's our second, so derivative of v with respect to x times our second x, plus the first, that's our v, times the derivative of the second with respect to x, that's 1. That's where this comes from. Let me clean this up, we don't really need that 1. So We write this as a function. Okay, cool, y over x, no problem. Make a substitution, v equals y over x, easy. Solve for y, not a problem. Why? Why are we doing that? Why are we solving for y? If we just replace the y's over x's with v, we'd have a problem with that y. So if we solve for y and take a derivative, now we get this idea of a kind of a double substitution. So think about what's going to happen. I know right now it's not vague, but it's not concrete because we don't have an example to work with. I'm going to show you that in just a minute. But if you had this all wrapped up in y's over x's, every instance of y is written as y over x. You can replace all the y's over here with v. But then dy dx, oh wait, if I take a derivative, I can replace the dy dx with this whole mess of garbage, all right? Not garbage, but the derivative of y with respect to x. Well, that'll work. So we kind of have this double substitution idea. We're going to replace the right side, have a whole bunch of v's and x's. We're going to replace the left side and have exactly this. Now, I need you to understand something. This is going to happen every single time with homogeneous equations. It has to, because if you solve for dy dx, and if you're making the same substitution every time, which you are with homogeneous equations, then this derivative is going to be the same every time. Then this dy dx is going to be the same every time. Then you're going to replace this with this every time. That's how homogeneous equations are going to work. After that, we'll hopefully be able to categorize this, whatever we get, into a basic integration or a separable equation, and then we'll go ahead and solve it with those techniques. So number one, write it. Number two, do your substitution. Number three, solve for y. Why? Why do we do that? Because we have to get rid of that dy dx, which means that we're going to have this. We're going to have this dy dx equals whatever we have here every time. And we'll make that substitution. After that, well, we're going to be substituting into this differential equation that we had. We just talked about that. All this is going to be v's and x's. All this is going to be this piece. That's what we mean by substitute into the differential equation. I'm going to make a little side note here that this should be, whenever you substitute, you should have no y's. So this should be in x's and v's only. If you have any y's, you've done it wrong. And that should be kind of obvious because we can only have our two variables here. We can't really have the y's and the x's and the v's. Then use a known technique. What I mean by that is something that we're familiar with. So use an integration if you can. Okay? Use separable equations if you can. Then, since you have only x's and v's, but you're really looking for y's, that's what this is relating to. It's saying, I want the derivative of y with respect to x. I sort of tricked the problem and wrapped it up in a v, no problem. But eventually we're going to have to unsubstitute that or resubstitute. So we'll resubstitute back to get our y. That's important. So we're going to be using this 2 times. So to get away from y, we put this as y over x and then make v. And to get back, we do v equals y over x. And then we'll be able to get our y's back. Lastly, just some notes. When you're doing this, when you're trying to write this as a homogeneous equation, you need to make sure that you replace all of the y's. That's a really big deal, including the dy dx, which is why this substitution works. After that, just know that when you're doing these substitution techniques, it's going to involve some trial and error, especially because some of them fit several categories here. So is it going to be frustrating? Yeah, it is a little bit. Don't let that anger you, though. Remember that psychologically what's happening is when you transition from frustration's okay. Frustration is your brain's attempt to cope with this new information. That's typically what happens. You run into it, you get a little frustrated, you slow down a little bit, your brain tries to organize your thoughts and put it into little categories. Piaget calls them schema or schemata, where you're trying to structure your knowledge. And then that can be frustrating because when something doesn't fit, you go, oh man, I thought I knew that, or now I'm having to reorganize this. But when you start getting angry at it, that puts up what's called an affective filter. It's kind of like when you're talking to someone, you both start yelling, you're like, well, I'm right. No, I'm right. And then, well, this is why I'm right. Well, no one's listening anymore. You're just yelling. and your brain's not really processing. You've shut down. And that's what happens when you get angry. So what I mean that is some of these can be just infuriating problems. When you start getting that, frustration's okay, all right? But when you're working on it and you're starting to get angry at your math, just stop, take a break, calm down, and then come back to it a little bit later. Otherwise, you're just going to waste your time and spin your wheels. So a little recap before we do our examples. We're now transitioning to try to make some differential equations that we don't know how to do into things that we do know how to do. Ways to do that are involved, we say those are substitution techniques for right now. One way we can deal with that is homogeneous equations. We have a couple other ones that we're going to go through as we move on. What homogeneous equations are structured as is when we can write y over x for every instance of y. If we can replace y over x with v and solve for y, that gives us not only a way to replace the y's, but a way to replace dy dx by that product rule combined with the chain rule on that implicit differentiation. Then when we do our substitution, we'll have x's and v's only. Use a technique to solve that, and then make sure, because what you're going to get here after you use that technique is, of course, x's and v's only. Solve back for y, so make sure that v, wherever you have it, is y over x, and then hopefully we can solve for y's. So I'm going to pause for just a moment. I'm going to write just one example up there. We're going to go through 3 of them, so we'll do one at a time. And then in the next video, we'll practice a whole bunch of them. Let's go ahead and start our first one. So, as we're going through these, I'm going to mention from time to time that this particular example can be done at least 2 different ways. Probably not like that, but this particular example can be done at least 2 different ways. So let's look at this from the scope of everything we know, hopefully wrap everything together. Is it a differential equation? Well, obviously, it's got a first derivative in there. Can you separate the variables? Oh, actually, let's start easier. Can you solve this for dy dx and take a basic integral? No, because as soon as I divide this, I don't have a basic integral. It's got x's and y's. Okay, can I separate the variables? It doesn't look easy to do that, so probably not. Is it linear? No. And if I try to write that as y to the first power, I have something over y there. So it doesn't fall into any of those classes right away. Can I do a substitution technique to make it fit one of those classes? Yes. Now, I'm going to talk right now about how this can be done 2 different ways, and in several videos from now I'm going to show you that. So remember this problem. I'll hopefully refer to it when I do it a second way, but check it out. This can also be solved with what I call an embedded derivative. For instance, if you can find the function of y whose derivative is also in the problem somewhere in the differential equation, you can make a substitution for that embedded derivative. Just remember, it's got to include all the functions. It's got to include all the y's. Here's what I'm talking about. Look here. Take a derivative of just y squared, all right? 2y. The derivative of y squared is 2y. That also appears somewhere in your, and we're getting a little more specific, but that appears somewhere else in your differential equation. When we have that, when the derivative of the function of y also appears in your differential equation, usually on the other side, we can solve it with an even easier technique. I'm going to get there in a little while, but I just want you to know that this can be solved that way. I will certainly come back and do that. So remember this example, because right now we're going to structure this as homogeneous, and I want to show it to you because of the 2 different ways. I also want to show it to you because it's a great example on what we can do with homogeneous equations. So number 1, let's try to make this in the proper form. Let's solve it for dy dx. No problem, we can do that. Let's just divide by 2xy. That doesn't look all that great. Maybe what we do is we split this up into 2 different fractions. Well, because remember what we're trying to do. We're trying to get y over x and y over x. This one's going to be a little funky, but maybe we can change it a little bit. We can always split up fractions when we have more than one term over one term. And if we simplify, then this, well, we get an x over y. Notice how this and that are completely gone. 2 and 2 and y with one of the y's. So we can simplify both fractions. And what I'm going to do, I'm going to structure this to try to get as close to possible as everything in, like multiplied by something that's a fraction, x over y or y over x. And like, well, wait a minute, x over y doesn't help us. It does help us, but we're just going to have to change it a bit. So when I look at this, I'm going to write this as 1/2, and then I'm going to write this as a fraction, x over y. And I'm going to think about this piece as something I'm going to substitute. Plus, I'm also going to write this as a fraction, y over x. Why do I put them in parentheses? Well, I'm doing that because I want to show that that's my substitution. In my head, I'm trying to organize this as something where I've wrapped all of the y's into y over x. All of the y's into y over x. Now, okay, so we said that does not look good. Let's try to make this homogeneous. Okay, solve for dy dx. All right, well, I know that involves fractions. Let's make fractions that simplify what we have, and then we've got to force this to be y over x. Because right now, that doesn't look good. You go, what do I do with that? Well, do you remember exponent rules? How y over x is great, x over y is the reciprocal of what I want. Well, we can always reciprocate a fraction by changing the sign of our exponent. So if that's x over y to the first power, then we could write this as y over x to the negative first power. So let's see, have we solved this for dy dx? It looks great. Have we structured it so that every instance of y is also y over x? So have we structured it so that we have all of our y's wrapped up into a fraction, y over x? Yes. This is what we're looking for when we do a substitution into a homogeneous equation. This is what we want. So let's do that. This looks really good. Here's y over x, here's y over x, the -1, a little bit funky, but not a huge issue. Let's go ahead, let's do our substitution. So our substitution for these homogeneous equations is always the same. What we're going to do is we're going to substitute v equals y over x. We're going to use that twice, once to get away from the y's, do all of our integration, and then once to get back to our y's. Now, how does it work? Well, if you watch the first part of the video, you know that we need to replace everything. Now, this is why we had to have this y over x. Y over x is going to simplify, substitute for v. Y over x is going to substitute for v. So every place you had y's, you've got to have it y over x to use the same substitution in every case. V and v. No problem. All you can possibly have is v's and x's here. On the left-hand side, we also need to get rid of this y right there. Well, that means that if we solve this for y, like we explained a few minutes ago, so we're going to use this twice and put a little asterisk here. If we solve that for y, and if we do a derivative on both sides with respect to x, we're going to get the same thing every time. I mentioned that, but maybe now you can see it a little bit more clearly. The reason why we're going to get the same exact thing every single time is because we're going to make the same substitution every single time. We're always, for homogeneous substitutions here, we're always going to write y over x. We're always going to make v equal to y over x in every place we see y. It's got to replace all the y's. We're always going to solve for the same y. It's always going to be v times x. That means the derivative is always going to be the same. Derivative of the first times the second plus the first times the derivative of the second every time. And now what we're going to do is we're going to do a double substitution. If you're reading through a textbook, this looks like, where did all this come from? So here's what's going to happen. I'm going to rewrite this. I'm going to show you where every piece goes. Every part in your parentheses y over x needs to become a v. Your dy dx needs to become this derivative. So when this changes, you go, okay, we're going to substitute a lot of stuff right now. This whole piece, remember that this and this, those are the same thing. When we do that substitution, we're identifying that if these are changing to v's, and that y is y, and that's wrapped up in your v, Well, then this dy dx that you get from that substitution is the same dy dx that we have in our differential equation. So if these are the same, this whole piece is going to go there. No problem. But if we defined our substitution as v equals y over x, then we're going to replace three pieces in this particular differential equation. We're going to replace every instance of y over x with v. We're going to replace dy dx with the same thing every single time for a homogeneous equation here. So on the left-hand side, we get x dv dx plus v. That should be pretty obvious because that's exactly what dy dx equals. On the other side, we get 1/2, no problem. V to the -1 plus v to the first. Usually, in what I've seen in a lot of when I do these lessons, I usually look at least 2-3 textbooks, look at what they're doing, make sure that I can explain it for you guys. But what normally happens is they'll say, oh, substitute, this is what you get. You go, where'd that come from? That's just a product rule with a implicit differentiation, and then you're substituting on both sides. The key idea here was we wrapped up x's and y's. Sorry, we wrapped up our y's as y over x. We found a derivative, dy dx, and we were able to substitute. So we said, all right, this is this piece, this is this, and then look at our problem. Do we have only x's and v's? Yes. So we've completely substituted out our y. Now we're going to have to substitute that back later, but here's the point. If you can do this, if you can structure this as y's over x's, then you always have the same derivative when you solve for y. Then you can always substitute for dy dx and for y over x. And then we're going to try to make this into a technique that we already know how to do. I hope this is making sense so far, because this is a pretty powerful technique. It's kind of cool that we're able to do that. There's just some key points that you need to know. All of your y's have to be involved in v's. So you cannot have any y's floating around. It doesn't work. Also, you only need x's and v's here because you're going to be treating this dv dx, as your new derivative. We're going to be trying to undo that. So v, x is still your independent variable that hasn't changed. V takes like your new y. So you're going to be trying to solve for v. Now that should work because if we can solve for v, then we have a direct way to get back from v into y. No problem. Let's do it. Let's see if this we can make something out of this that we already know how to do. One thing you might want to do is just start simplifying. So this happens quite a bit too. This is fun. What if you subtract v? Well, then this is all gone. Then we get x dv dx equals, I'll probably write this as 1 over 2v, just because that looks a little bit nicer instead of v to the -1 power. You go, oh, wait a minute. Hey, that's v, that's dx. There's an x, there's a 1 over 2v. If I divided by x, I'd have a separable equation. So, can you group your v dv on one side, your x dx on the other side? Yeah, that's a separable equation. Let's do that. So let's multiply both sides by 2v. I'm sorry, just v. Let's keep our constants on the x side like we talked about. So we'll multiply both sides by v. We'll leave the 1/2. We'll divide by x, and then multiply by dx. That sounds like a lot, but it's not all that bad. So if we multiply by v, we get v dv. If we keep the 1/2, we get the 1 over 2. If we divide by x, we'd have 1 over 2x. If we multiply by the dx, remove the dx, we get, and hopefully you can do this on your own, we're just structuring our variables in the place that they need to be for separable equations. Your dependent variable, d, the dependent variable, so v dv in this case, and then on the right-hand side, your independent variable with dx, so x dx. And now, man, we should be really familiar with this. We've done a ton of examples on this. Just take an integral. On the left-hand side, when we do that, we're going to get v squared over 2. On the right-hand side, oh, wow. On the right-hand side, we'll get 1/2 ln absolute value of x plus c, of course. And we talked about c quite a bit, how we can deal with that. Another thing that we can do, start solving for v. I really wouldn't, I wouldn't plug in y over x right now to v until I got it as simplified as I can with the v's. So I'm going to multiply everything by 2 because I don't want to deal with a square root of x over there. I want to deal more with just, well, multiply by 2 and then we don't have to deal with the square root at all. So if I multiply both sides by 2, we get v squared. We get ln absolute value of x plus 2c1. Do you remember talking about the constants, how when we have a constant, well, a factor that's a constant times c1, we can wrap that up into a larger, quote-unquote, larger arbitrary constant? We can do that a lot, and we can do that here. So v squared equals ln x plus c. Now, the last thing that we do, we use this substitution to, let's go through the whole thing. We use this substitution to get rid of y's, no problem. We also got rid of dy, that's perfect. We made this into a separable equation. Then we can separate our variables. We can do a very basic integral on both sides. We can get our arbitrary constant taken care of, but we need to get back to our y's. And that's where this substitution comes in really handy. We write it down and we use it 2 times. One to get away from y's, one to get back to y's. So if v equals y over x, man, v still equals y over x. Okay, well, let's square both y and x. We know that exponents distribute across one level, operation level below, so exponents distribute across multiplication and division. If we multiply by both sides, multiply on both sides by x squared, we get and sure, you can distribute that, get x squared ln x plus c x squared. We really wouldn't take the square root and do a plus and minus unless you had some specific restrictions on your domain. Sometimes, by the way, they do that. They'll say stuff like, hey, assume that x is positive, assume that x is greater than 0, and then you would drop the absolute value. So that can happen. The domain is a big part of differential equations. Sometimes even a different domain, you get a different solution. And we sort of talked about that when we started the introduction to this, how that can happen, especially with particular solutions. So anyhow, we're done. That's about it. And that's kind of cool. Notice how we got back to y, we don't have any v's. That's how homogeneous equations work. I'm going to give you a couple more examples now, and then we're going to practice just the heck out of this in the next video. Let's give this a try. So we have another differential equation. We're looking at it, we're saying that does not look like anything I'm familiar with. It doesn't look linear, it doesn't look separable, it doesn't look like a basic integral. So let's go through and see if we can substitute. A good hint that you have something that is that's homogeneous is when you have y or functions of y with no negative exponents over here, and you have an x over here. And when you divide it, you'll be able to create these fractions y over x. That's a really good hint that might be a good way to go. Does it always work that way? No, and that's why I said you might have some trial and error, and that's okay. So when we're working through these, expect that you might make the wrong substitution and have to go back and fix it. Frustrating? Yes, but it's part of learning. So when I'm looking at this, I'm thinking that does not look like anything that would be a basic technique that we have. Maybe we can make a substitution to force it to be one of those techniques. If I start dividing by x, I'm going to get a y over x. Oh, okay, hey, that looks like homogeneous. I'm going to get a y over x here. Maybe we can make that work. Let's give it a try. So dividing everything by x, y over x looks pretty good. Square root of x y over x looks, here, that doesn't look good, Leonard. That looks like crap. It does, but maybe we can force this thing to become a y over x. Think about what x could be represented as. Instead of x, couldn't we just do x squared? Couldn't we just do that if x is positive? And so you might see a domain restriction here, like, hey, assume that x is positive so you can make this substitution. Otherwise, you have the this right here, the actual solution here would be absolute value of x. So that's an even power, an even root, and an even power. The absolute value of x, and that's only equal if x is greater than 0. So you might see a domain restriction on some of these problems. Some textbooks just flat out omit them. That would be an issue, but some of them don't. So you'd say, okay, well, for this to work, this would be x if x is positive, negative x if x is not positive. So we'd have to look at the domain there. For us, let's say that x is positive and we're going to make that substitution. I just want to do a little side note there that sometimes you'll see this without any explanation. Right or wrong, that's not technically right, but that's what they're doing right there. So we'll go, okay, yeah, let's just call this the square root of x squared. Fantastic, because if we can do that, if x is equal to the square root of x squared because x is positive there, well, then we can write this as one big square root. And we would get xy over x squared. Oh, hey, that looks a lot better because now when we simplify a fraction, we get exactly what we're looking for. We get every instance of y is wrapped up as a fraction y over x. We get, if we do a substitution to eliminate this, to say v equals y over x, v is still a function of x fundamentally. Well, then when we take a derivative, we can also wrap up that dy dx in this double substitution idea that we use for homogeneous equations. So let's show that substitution. I show it every time. The reason why I show it every time is because I don't want to lose track of what I'm doing. So I always write whatever substitution I'm doing. I always do the derivative. So I always solve for y. Do you have to do that? No, probably not. And once you do this about 1,000 times, maybe it takes 5 times, you start seeing the pattern. You go, yeah, I know that this is going to be x times dv dx plus v. I know that. I know this is going to be a v and that's going to be a v. If you can do that, awesome. I show it because I don't want to make mistakes. I'm showing how to explain it to you so you can see what's going on every step of the case, step of the way. Also, if you're taking notes right now, I would strongly encourage you to do that because you all know that like 4 weeks from now, if you see this one time and you're not practicing it, or you have practiced it but then you move on to something else, your notes aren't going to make a whole lot of sense. So show it now, that way later on you can refer back and go, oh, that's what I'm doing. So in our case, dy dx happens the same every time. Creates for us this other piece of the substitution. So from right here, I'm not going to write it twice, I'm just going to substitute from right here. Dy dx is this piece. Y over x is v. Plus sign, 2, square root. Y over x is v. Hey, we've done it. We've wrapped up every instance of y in some form of v and x. That's great. Now we can simplify and see what comes out of this. So let's subtract v. We always want to make sure we're simplifying before we try to structure. This is one technique that we already know. On the right-hand side, v's gone. We just get 2 square root v. And again, we see that this is all multiplied and divided. So, or divided if you divide by x. So what we have here is this separable equation again. Let's get our x's on one side. Let's get our, with dx. Let's get our v's on the other side with dv. So I'll be dividing by the square root of v. I'm leaving the 2. I'm dividing by x, and I'm moving my dx. Divide this over, group our v's, dv's, leave our constants where they're at, constant factors where they're at, divide by x, move your dx, and now we can take this integral. So when we take our integral, you might want to write this a little bit differently. So instead of 1 over the square root of v, it looks a little awkward. Let's write this as v to the negative 1/2 power. When we do our integral, man, these are some basic ideas. This is great at this point. Let's add 1. Divide by the new exponent. You might be asking this too, do we need a plus c over here? We already covered that when we talked about separable equations. You don't. Because if you had a plus c here and a plus c here, you just add or subtract. There'd be different c's, potentially. You'd add or subtract them, and then group it into a larger, different arbitrary constant anyway. So v to the 1/2 over 1/2 equals 2 ln absolute value x plus c1, because I guarantee we're going to be changing that based on having to multiply here. So let's try that. Well, if we move that, so v divided by 1/2, that's the same thing as 2 square root v. So something divided by 1/2 is 2 times whatever that is. If we divide everything by 2, we're going to wrap that piece up as the plus c. So let's do 2 things. We know that we've solved pretty much as we can for v. Let's go ahead and replace v with y over x. You could square both sides right now if you wanted to. That's not, maybe we'll do that. So let's square both sides. I'm wrapping up the c sub 1 over 2 as c. I'm squaring both sides. So square root of v squared ln absolute value of x plus c squared. And now we say, well, that's not good enough because we started in y's. V has y's in it. V is a function of y and x. So let's replace it. If v equaled y over x, then y over x equals whatever v is, transitive property. If we multiply both sides by x, we're good to go. The reason why people like homogeneous equations so much is because they're very predictable. If you can solve it for dy dx and have y over x, the substitution works out the same every way. And that's very nice because you go, yeah, this is going to be here every time. This is going to be a function of x and v every time. Are they always this easy? No, they're not. But they're at least predictable. You know what's going to happen with them, and you know what your substitution is going to look like every time. That's why people generally like them. So let's try one more for this video, and then I'll give you some more advanced concepts in the next one. So what you should be getting out of this is that the structure works the same way every time. What's necessary is that you wrap up your y's as y over x's, all of them, and then substitute y over x equals v. That lets you make a substitution for dy dx by taking a derivative of that. So solving for y, taking a derivative. And then we get this hopefully separable or basic integration for the technique of solving it. Let's do one more. Okay, great problem to end on. Lots of stuff going on here. You know what I like to do. I like to give you problems that involve lots of things because I know that some of you have forgot some of these concepts of integration, like tan inverse, which we're going to get here. That involves tan inverse? Yeah, it sure does. And some separation of some fractions and some basic Integration. So I like to give you these things because I think they're challenging and you're going to see them. And sometimes teachers just love to trick you and go, oh, you didn't see that one thing. Why did they do that? I don't know. But it does come up. And so I'm going to show you this example that has some more advanced techniques as kind of a segue to the next video. So number one, let's look at that for what it is. It's a differential equation. It doesn't look like anything that we could easily do. So what I mean by that, it doesn't look like if I solve it for dy dx, I can just take an integral. It doesn't look like it's separable right now, or at least not easily. It doesn't look like it's linear, at least not easily. It's got some fractions going on. So can we do a substitution technique? Well, we're going to try. Which one? There might be a couple, but the easy one, the one that you see would be the easiest one that you can do at that time. Can you try a few of them? Maybe. But let's go ahead, let's try homogeneous. Why? Well, it's very predictable. We know what's going to happen. And so let's go ahead and try to make this of that form. So let's solve for dy dx. Okay, that looks worse than what we had before. Maybe, but remember our goal. Our goal is to get all of our y's over what? Over x's. So if we want to get all of our y's over x's, maybe we just divide by x everywhere. You can think about this as if I multiply by 1 over x over 1 over x, same thing as long as x is not 0, so we'd have to say that x is not equal to 0. But as long as we do that, well, that means that if you were to distribute, you can get x over x plus y over x plus x over x minus y over x. You might remember back to Calc 1, we did that a lot in limits, a lot of the times in limits. And so what we're doing here is kind of the same idea, but we are always looking for y over x in homogeneous equations. Let's just force that to happen. Let's divide everything by x. You're going to see this technique quite a bit. A lot of problems involve, well, not a lot. Sometimes problems involve this, and you get this, this idea that if you divide everything by x, not only will you simplify some parts of this, you'll also force what you want. You want the y's to be over x in every case of y. Let's just do that and see what happens. This happens a lot when you have fractions like that. So simplifying. Well, our dy dx would equal 1 plus y over x. Oh my gosh, the y over x looks perfect. And then 1 minus y over x. I always put my y over x in parentheses with homogeneous. I always think that that's going to be v, that's going to be v. I've wrapped up all of my instances of y's in something over x, and now I can make my substitution. I always write my substitution. I always know that I'm going to use it twice, no problem. I always solve for y. Do I need to do that for me to do this problem? Not really. I could probably just from here in my head. Why? So that I remember it, so that my notes make sense, so that I can go back and go, oh yeah, that's what I'm doing. On the left-hand side, dy dx. On the right-hand side, product rule with a chain rule on v as an implicit derivative. And now we make our substitution. Dy dx, this piece, is going to become this piece. So on the left-hand side, this becomes x dv dx plus v. This is dy dx. That's this piece. On the right-hand side, I have my 1 still. I have my plus still. I have my 1 and my minus, but the things in parentheses, I've structured them so that we know that y over x is v. Now, okay, I've got rid of all my y's, even my dy dx, and that looks really good, but the problem looks not so good. So let's try to do a couple things to organize this. Maybe if we're trying to do separable equations, let's move our v over. Let's try to combine those. So if we subtract v, we get this x dv dx equals 1 plus v over 1 minus v minus v. Now, if we're going to do something like separable equations with separator variables, we're going to need one fraction here. So we're going to take the time and we're going to write that as one fraction. We're going to need a common denominator. So let's do that. If we're going to make a common denominator, we know that we'd multiply by 1 minus v over 1 minus v. We need the common denominator. Okay, starting to look a little nasty here, but let's see what happens. So 1 plus v over 1 minus v minus, I never distribute this right now, ever, because I'll miss that sign and I won't get the plus v squared that I should have. Okay, so I'm not going to do that. What I'm going to do is I'm going to write this as one fraction, so I know I have a common denominator, and I'm going to write minus v, 1 minus v. So common denominator, yes. Original numerator, yes. Second numerator, yes. And now we distribute with the minus. Sign errors will absolutely kill you on these sort of problems. Don't do them. Go slow enough that you don't make the simple mistakes. So when we organize it, when we combine some like terms, right-hand side we'd have 1 plus v minus v and plus v squared. 1 plus v minus v plus v squared. Let's move up here. So when we combine some like terms, we've got our x, we got our dv dx. That side looks okay. Right-hand side we have 1 plus v squared, or v squared plus 1, over 1 minus v. Now, that is a separable equation. So let's do that. Let's put our v's on one side. We've seen this before in the, I did so many examples, it's gotta be in there somewhere, where when we do this, we'd multiply by the reciprocal here when we move our v's over. So we'd multiply by 1 minus v, we divide by x squared plus 1, we divide by x. So when we move this over here by multiplication and division, we're going to get the reciprocal dv. On the right-hand side, we have to divide by x dx. Let's let that sink in for a little bit. Hopefully you're with me on this. Multiply by 1 minus v, check. Divide by v squared plus 1, got it. Leave the dv. Divide by x, got it. Move the dx. Now we take our integral. When you're doing integrals, this goes back to Calc 2, don't try to do the hardest technique available. Try to do the easiest. So when you look at that, you go, trig sub? Sort of, yeah. But not directly, not right now, because that's nasty. U sub? No, it's not that, because the derivative here is 2v, and this up here is 1 minus 2v, so we don't have enough variables down here to make that happen. Our signs are wrong. What else could I do? Well, maybe we split it up. So let's split up that fraction. Instead of trying to do partial fractions or whatever, this is already an irreducible quadratic. That's already on linear. It's not going to really do anything for you. Let's go ahead and split the fraction. So when we do that, we have 1 over v squared plus 1 minus v over v squared plus 1. All of this is dv, and we have integral of 1 over x dx. Right-hand side, very nice. We're just going to get ln absolute value of x plus c. On the left-hand side, now we have some things that we can do. So this, use your table. Use a trig sub if you really need to, but use your table. That's going to be tan inverse of v. Then, so I know this guy, tan inverse of v. Then we do have a substitution. We know that that's going to be u equals v squared plus 1. All right, du equals 2v dv. If we divide by 2, got a nice substitution on that fraction. So we have the integral, I'm going to do it right up here. Integral of 1 over u, and then du over 2. Let's see if that makes sense. We have v dv equals d over 2, so this piece, d over 2. We have this v squared plus 1 is u, no problem. And so this is going to give us one half, that's the d over 2. ln, that's 1 over u, and then u is v squared plus 1. So let's put that back. Since v squared plus 1 is never negative, we don't need the absolute value. On the right-hand side, we do. And I hope that makes sense. You might want to pause and go through that. Make sure that you can see that this is tan inverse. Trig sub or table, I would use table, or memorize if you want to. I don't suggest it, but that you're going to do it so often, it's going to end up being memorized. This is a nice u sub. So we got that by splitting that up. Try easy techniques rather than harder techniques. So we'll do a u sub. We're going to get this minus 1/2 ln v squared plus 1. And then, man, that's going to be pretty nasty if we try to solve that for v. Are you seeing that? Might not even be possible. I mean, we have a natural log, we've got a tan inverse, v's inside both of them. So in these sort of cases, most of the time, we don't even solve for v. And if we're not solving for v, we're probably not going to be able to solve for y either. So we do need to substitute back in, but then we're going to be done. So if v equals y over x, then we're going to have a tan inverse y over x. Looks great, relatively. 1/2 ln v squared means y over x squared, or y squared over x squared. Plus 1. I'll probably use a bracket around that, make it look a little neater. Equals natural log absolute value of x plus c. I know it doesn't look nice, but that's about as nice as we can make it look. Otherwise, we're starting to try to undo a natural logarithm and a tan inverse at the same time, and we're going to run into some major issues. So the whole process boils down to we can't do these differential equations with the basic techniques that I've given you so far. So now we're getting on into substitution. Can we make it look like one of those techniques with a basic substitution? Homogeneous is the first class of those that we're looking at. Is it the first one that you should try? Not necessarily. People like it because it's predictable, but not necessarily. Some of them can be done several different ways, and we need to take a look at some of those other ways. Sometimes you get an easier way rather than homogeneous. This didn't seem all that bad, but look at all the work that we have to do to structure it. Sometimes we can get away from that. So structuring this is imperative for homogeneous. You have to wrap up every instance of y as y over x. That has to be the same substitution. All the y's have to be wrapped up in v's. That way the derivative makes sense. That way we can actually find the dy dx. That way we can do our substitution. And then what that does, hopefully, if you've done it right, that'll make something that's possible in a different type of differential equation with v's in it instead of y's. And that should be in the form of a basic integral or a separable equation. I hope that made sense. Next video, we're going to do a lot of examples. So I mentioned I was going to do this a few videos, that at the end of certain videos where we dealt with a new technique, I was going to come back and say, now we need to consider domain. So we've been focusing only on technique, but this domain is important. We looked at linear first order differential equations and saw that sometimes we have some domain problems when dividing by a variable. That happens here too. And also on the integrating factor, because we don't want to deal with some absolute values sometimes and for some domain problems that occur. Well, the same sort of thing happens in these three problems. So I want to look at them very quickly just so you understand what's going on, why we're seeing some domain restrictions. And this happens when we start rewriting differential equations to fit a technique we're trying to use. So this first one, man, the first thing you're going to have to do is divide by 2xy to make this fit the technique. I'm not showing the whole problem, but obviously we're dividing by two variables. We just need to understand that those two variables cannot equal zero. Either one of them. By the zero product property, each factor could equal zero, making the whole product equal to zero. And so all we have to do here is say, all right, well, hey, x, yeah, that can't equal zero, and y also can't equal zero. Otherwise, we'd be divided by something that could equal zero. And so we talked about this domain thing, where when you're trying to fit a differential equation to a certain technique that you're trying to use, in order to make the technique work, you're going to have to put some restrictions on your domain. Now, right or wrong, that's what we have to do in order to make the technique work to solve this. And so we're saying, I can solve it. Okay, I can do this, but I've got to have these two things be satisfied. And that's where those domain restrictions come in. Now, you might be wondering, well, wait a second. On the linear, we always had it greater than zero. What's the difference? One of the differences is that on your linear, when you solve them, you create this product rule and you integrate and you get an x or some function of x over there, and you get a function of x on the right hand side. And we like to simplify those, and that works very, very well for us. When we're dealing with homogeneous equations, they're always going to yield for you some sort of a separable equation. That's how we solve all of these. That's what the product is. It's this product it's this substitution that creates this product for us that we do separable equations with. And so what happens in those separable equations, if you think back a while ago, we did one of two things. We either wrapped up that absolute value as a plus or minus e to the c. That happens a lot. Or what we did is we had the absolute value in some other expression where we couldn't simplify it anyway. And so one of the reasons why we don't do the greater than zero is because when we're getting this ln absolute value of x, either we can wrap up the e to the ln, we could wrap up that absolute value in a plus or minus. And so we'll get this, the same sort of idea with the separable. We'll get this, the c, okay, yeah, but then when I raise this to the e power on both sides, I could do the plus and minus e to the c, call that c1, call that thing a big C, and go, okay, well, this is my constant, and I don't have to worry about the absolute value. Or we have I have ln of an absolute value, or some function with an absolute value in there that I wouldn't be able to simplify anything with anyway. And so we don't really, that's one reason why we don't want to do this here. Unlike the linear, we're not having those cases. We don't have the opportunity to wrap up the plus and minus from the absolute value with an e to some constant. We don't have the opportunity. It's not separable. It's linear. It's a different thing here. And so when we're dealing with these separable equations based on these homogeneous equations that we were solving, well, we have the opportunity to do two things. Number one, either wrap up the absolute value in that plus and minus e to the c sub 1, or we don't get to simplify it anyway because it's ln of some absolute value. We can't simplify that. And so any other x's, extraneous x's, wouldn't come into that ln anyway. And so for those two cases, we really don't worry about it. So long story made really short, for linear, a lot of times you're going to get the x's greater than zero because of the things that I mentioned. Here, we're not going to do that for the reasons why I mentioned. And so for homogeneous, you go, yeah, you know what? I can't have x equals 0. I can't have y equals 0. Do we care about the absolute value? Not really, because either we're going to wrap that up in a plus and minus e to some constant, or we probably won't be able to simplify that that absolute value of x with any other x's anyhow, because it's going to be wrapped up in another function. And so we're going to leave it. Same thing happens here, so very quickly. Yeah, you're dividing by x. Wait, so x can't equal 0, right? Yeah, great, x can't equal 0. But wait a minute. We have x times y inside of a square root. Don't those always have to be positive? Doesn't that product have to always be positive for real numbers inside of a square root? Yeah. Well, that implies right there that x can't equal 0 anyway. So this one's all we really need. It says, yeah, hey, if x is 0, this wouldn't happen. So x can't be 0 in order to make this happen anyway. The zero product property. Last one, the first thing we do for the homogeneous, and you saw this in the last example, we divide by x minus y. Wait a minute, we're dividing by x minus y. This is going to yield two conditions. One of them is, if you're going to divide by something, that something can't equal 0. But furthermore, because we have this homogeneous equation, we're setting these all up as y over x, x also can't equal 0. So that gives us two conditions that we've got to restrict our domain in order to make this technique of homogeneous equations work. I hope this is making sense to you. This is why I didn't really want to go through it when we were going over the technique. It just would have felt very choppy. It would have felt very choppy, like, oh, now we got to pause and explain all this stuff. So I wanted the technique just to flow, and now we have this, well, but you're dividing by something that can't be 0. Say that. Say, can't have 0 for x and y. Say, that can't be negative or 0 because, okay, it's got to be greater than 0. We're divided by x and that takes care of it. Here, you're dividing. Hey, the thing you're divided by can't be 0. Also, the thing you're dividing by can't be 0. We're just defining that. Again, this differs from linear, where we had a lot of x greater than 0. Now we just have the x not equal to 0 because we're not as concerned with the absolute value. Not concerned as much about the domain as well. From some of the issues that we get. So separable equations help us out a little bit with that. Anyhow, I hope that's making sense. You're going to see this a couple more times in several more videos that we go back and talk about domain at the end. Method first, technique first, then we discuss domain. Have a good day.